Peace be upon you and God's mercy and blessings. In the previous lectures, we talked about differential protection and started with the Merz price configuration. We looked at the challenges we faced during the application of the Merz price configuration and how we were able to overcome these challenges using the bias differential configuration. Today, we want to see together how I can use the bias differential configuration to protect equipment like transformers. In fact, transformers are among the important equipment that must be well understood because they have a set of aspects that need to be comprehended so that you can achieve what is intended here, meaning that you can obtain without. And also, you can obtain a stable system during normal operating conditions without any maloperation. And also you can obtain a trip during, let's get to know the first thing we have, which is simply what it means to have different current K-ohm values on both sides of the transformer, and this, of course, the magnitude. Simply put, I have different current values, meaning different current values on both sides of the transformer, and consequently, as per the transformer winding configuration, you simply put, as we all know, if I have a step-up transformer for voltage, it will be a step-down for current, and if I have a step-down transformer for voltage, it will be a step up for current. Let's look at a simple example of this. If I told you that I have a DN1 transformer and this transformer is step down, the power of the transformer is 60 MVA. The voltage on the high side is 132 kV and the voltage on the low side is 13.8 kV. If we calculate the current on the high side and the current on the low side, the current on the high side will equal the apparent power, S, divided by the square root of 3 times the voltage on the high side, and the current on the low side equals the apparent power, S, divided by the square root of 3 times the voltage on the low side. Consequently, as we can see, the current on the high side is 262 amperes, and the current on the low side is 2510 amperes. This means that now at the transformer, if a current of 2510 amperes is drawn on the low side, a corresponding current of 262 amperes will flow on the high side. So we can see now that the currents in the primary circuit are actually in different natural states. And this will lead us to the second point, which is that you will have difficulty differentiating between the currents. What does this mean? It means that now, in order to differentiate between these currents on the current side, you need a current such that its value converts to 1 ampere. Get me a transformer that converts 262 amperes to 1 ampere. And compare another transformer that converts approximately 2510 to 1 ampere, and thus you can compare the 1 ampere on the high side and the low side. And of course, this is not what is usually present. You typically have a current transformer at the stations. Say, for example, practically speaking, a CT ratio of 300 to 1 on the high side and another CT with a ratio of 3000 to 1 on the low side. So this is the first problem or challenge we encounter when applying biased differential on the transformer. Let's see together what the second problem will be. The transformer vector group or the directional group of transformers actually causes two problems for me. The first problem is I-node elimination. What does I-node elimination mean? For example, if I told you I have a transformer D-Win or a transformer YND and so on, the important thing is that one of the sites in your transformer is star grounded. Star grounded means it allows the passage of I0 or I-node, which is the zero sequence current, or the I-node or the zero sequence current, while the other side of the transformer, whether it is delta or star node grounded, will not allow the passage of the I-node or zero sequence current. Let's take an example of this. If I told you that I have a DYN3 transformer, and I specifically mean to talk about a DYN3 transformer, of course we are all familiar with DYN1 and DYN11 and YND1 and YND11 transformers, but here I have another purpose I want to convey to you. Let's say an external single phase fault occurs on the star side on phase A. As a result, since this is star grounded, it will allow the passage of the zero sequence ground or this ground fault voltage. Consequently, the current flowing through phase A will be detected by the CT of phase A. And considering that the current of phase B and the current of phase C are negligible, let's say zero current, I will now only have current from phase A on the star side for my protection relay. Alright? So, due to my vector group, which is D13, I will notice the following. For phase A to carry this current, it will draw from phase A, but here the external terminals of phase A are connected to phase B and phase C. And as a result of not having a neutral on the delta side, for current to pass through your coil or your phase A, it will have to draw current through the cables or from outside the transformer, meaning through phase B, and return from phase C. Here, we will notice that phase A, or the current read by the current transformer in phase A, is not actually reading current from phase A in the delta. That's the first point. The second point is that it reads from phases B and C from two other phases. The third point is that you have one phase being read here and two phases being read there. Look at the number of challenges you are facing now and need to solve. In other words, we know that it is being monitored, and opposite it from the other side. So imagine now that you are saying that the current read from phase A on the star side does not actually have a corresponding current from phase A on the delta side. And also there is a current flowing in phases B and C on the delta side, but there is no corresponding current in phases B and C on the star side. Additionally, here you have only one phase, and here you have two phases. This is, of course, the problem we refer to as node elimination. And of course, we have different vector group connections, such as DN1 or DN11 and so on. There are many connections, and as we can see in the diagram, in front of us it shows, for example, DN1 with an alpha like this, which is configured M-bit in this way. When you draw current from phase A on the other side, where will you draw from? From the cables or from outside your circuit? You will draw from phase A and C, and so on, depending on the different vector group you have. And of course, as I told you, we will, God willing, learn in detail, regardless of this diagram, how to wind the transformer, how to deduce the connections for the external terminals of the transformer, how to understand the directions of currents in the transformer, and even how to do it with the phasor diagram without even drawing these shapes in front of us. The second problem it causes is, what does this mean? Due to the different differences or variations you have, like in the angles between the transformers, the high side and the low side of the transformer. Let's take an example of this, the transformer we just mentioned, which is DN3. When it's written like this, the first letter you have, which is the capital letter, is the primary or high voltage winding connection. And the second letter, which is the small letter, is the secondary or low voltage winding connection. And the N means that the secondary neutral is connected to the ground here. Additionally, there is a number here, and this number represents the phase displacement of the secondary winding with reference to the primary windings. Usually this number is multiplied by an angle of 30 degrees, so 3 times 30 equals 90 degrees, meaning that the star side leads the delta side by 90 degrees. That is, if we draw it in the shape of our clock, or the hour, and say that you have here the time is 12 or 0, 1, 2, 3 and so on, then we notice that the phase on the high side says it stopped at 0 or 12 o'clock, your reference, so you will find that on the star side, you will find that this phase is refracting the phase opposite it on the high side by how much? By 90 degrees or 3 by 30? By 90 degrees or 3 times 30? The third and last thing we have is the transformer tap changer. The transformer tap changer is a mechanical device used to change the number of turns on one side of the transformer, which is the high voltage side. Consequently, the overall turns ratio is changed, which of course helps in regulating the voltage. However, as a result of using the tap changer, there is a mismatch in the differential currents, which may lead to differential maloperation. In fact, there is a very excellent video using MATLAB Simulink that explains this point to us. But before we talk about the video, we would like to thank the creator of this video, which is the EEEB page led by engineer Hani Kamel. The idea is quite simple. Here we have a step-down transformer from 132 kV to 13.8 kV. To 13.8 kV, 30.8 kV. So while the voltage taps are changing, you have changed from tap 1 until we reach tap 25. As the taps basin change, we can see here the currents changing towards the high voltage and low voltage sides. At tap 25, the high voltage current reaches 1.1 per unit, while the low voltage current is 0.89 per unit. As we mentioned, this can lead to differential maloperation. I will leave the link in the video description so you can go back and watch the full video. With this, we have reached the end of the lecture, and hopefully next time we will see together what solution will be used to overcome the transformer differential challenges to properly apply bias differential protection on transformer equipment. To properly apply the bias differential protection on transformer equipment, thank you.